Namaskaram. In last class, we have seen that critical points of a two-variable function. In this session, we will discuss a second derivative test to determine the behavior of the two-variable function at a critical point, and as analogous to our one-variable case. Solution of last homework. This is the result. Let f of xy be a function of two variable and x0 y0 be a critical point. Then we define capital D is like this: fxx at x0 y0 into fyy at x0 y0 minus fxy square. Okay, this means partial derivative f with respect to x 2 times. Okay, and so we calculate this D at a particular point, at a critical point x0 y0. Then first case, if D is positive and fxx at this point is positive, then f has a relative minimum at that point. Okay. And second case, again, if D is positive and fxx is negative at that point, then f has a relative maximum. Clear? And third case, if D is negative, then no need to check the nature of fxx. Whatever be the nature of fxx, if D is negative, f has a saddle point. Okay. And we have one more case, D equal to 0. Then there is no conclusion. That means in this case, maybe it has a relative maxima or relative minima or maybe a saddle point. Okay. So in the case of D equal to 0, we have no conclusion. We have to we have to use further analysis. Okay. Consider problem. Locate all relative extrema and saddle points of this function. So we have to find all the relative maxima and minima and saddle points. Okay. So we are going to apply our second derivative test. For applying our second derivative test, first of all we have to find the critical points. Okay. So find fx and fy and equating to 0, then solve. So what are the critical points? Okay, our fx is equal to 6x minus 2y and fy is minus 2x plus 2y minus 8. To find the critical points, we have to equate these two equal to 0. So now we have two equations and two unknown. By solving these two equations, we get x and y. Okay, so what is x and what is y? Yes, x is 2 and y is equal to 6. So this problem has only one critical point, that is 2, 6. Okay, next we have to calculate D at this point, at this critical point. And what is our D? Okay, so D is fxx at this critical point 2, 6, fyy at 2, 6 minus fxy whole square 2, 6. So first of all we have to compute what is fxx and fyy and fxy. Okay, and what is fxx? We have fx, so you simply differentiate this fx with respect to x, so that is nothing 6. And what is fyy? Differentiate this fy with respect to y, that gives 2. Then fxy, either you can differentiate fx with respect to y or fy with respect to x, whatever be the answer is same. So if you differentiate this fx with respect to y, this become minus 2, right? So these are the three second order partial derivatives. Okay, next we have to substitute all these values at this point, because our second derivatives are constant. So whatever the point, this value remains same. So this is equal to 6 into 2 minus fxy square, that is minus 2 square. And this is 12 minus 4, that is 8. Okay, so our D is positive. Also, what is our fxx at 2, 6? fxx is 6 throughout 6. So at 2, 6, this value again 6. So this also positive. So what is our conclusion? D is positive and fxx is positive. So by our second derivative test, okay, this is our second derivative test. If D is positive and fxx is positive, if both are positive, then f has a relative minimum at that point. Okay, so at 2, 6, this function has a relative minimum. Clear? So f has a relative minimum at 2, 6. Okay, this is the geometrical representation of this given surface, and it is clear that it has only one lower point. Okay, at only one minimum point. only one critical point, that is at 2 6. Okay, and that is our relative minimum. Okay, this is the geometrical representation of this one. You can plot such 3D surfaces using matplotlib. It's a library of Python. Consider the second problem. Locate all relative extrema and saddle points of fxy is equal to 4xy minus x raised to 4 minus y raised to 4. Okay, so first we have to find the critical points. So what is our fx and fy? So fx is 4y minus 4x cube and fy is 4x minus 4y cube. To find the critical points, we have to equate these to 0. So this implies you can take 4 outside and cancel. So this become y minus x cube equal to 0. This implies y is equal to x cube. Similarly, from this equation, we have x minus y cube equal to 0, and this implies x equal to y cube. And we have to solve these two equations. Okay, so what is our y? Y is equal to x cube, so you can substitute. So this become x cube whole raised to 3, that is x raised to 9. So this become x raised to 9 minus x raised to 9 minus x is equal to 0. So how to solve? We have to find the real solutions, right? We can take x outside, so x into x raised to 8 minus 1 equal to 0. A product of two things equal to 0 implies either x equal to 0 or x raised to 8 minus 1 equal to 0. X raised to 8 minus 1 equal to 0 means x raised to 8 equal to 1. So either x equal to 0 or x raised to 8 equal to 1. And we have to find the real solutions, right? Because our x and y are real numbers. So x raised to 8 equal to 1 means what? Either x equal to 1 or minus 1. So x has three choices: 0, minus 1 and plus 1. So what are the corresponding values of y? You can easily find value of y from this equation. When x equal to 0, y value is 0. When x equal to minus 1, y value is also minus 1. When x equal to 1, y value is 1. So our critical points are 0 0, minus 1 minus 1, 1 1. These are the three critical points of this function, right? Okay, next we have to check the nature of these critical points. Okay, for analyzing the nature, we have to calculate our d at all these 3 points. Okay, so find fxx and fyy and fxy. What is fxx? Fxx is nothing. You differentiate this fx with respect to x, that gives minus 12x square, and fyy, you differentiate this fy with respect to y, that is minus 12y square, and last one is fxy, differentiate fx with respect to y, that gives 4. So these are the 3 second order partial derivatives. Next we have to compute this d at all of these 3 critical points. Okay, we can compute this by a table. So consider this table. So first our critical point is 0 0. What is fxx at 0 0? You simply substitute x equal to 0, fx is 0, fyy is 0, and fxy is constant. So whatever be the point, this value is always 4. So next we compute the d using this formula, right? So d value is equal to minus 16. Next we consider second critical point, that is 1 1. At 1 1 our fxx is minus 12. Why? If you substitute x equal to 1, this become minus 12, and fyy is minus 12, and fxy remains 4, and d value is 128. It is positive. And in the case of minus 1, these are the corresponding values, and d value is equal to 128. Okay, so what is our conclusion? At 0 0 our d is negative. That means 0 0 is a saddle point, and at these 2 points our d is positive and fxx is negative. So that means these 2 points are relative maxima. Okay, so that is our conclusion. Okay, this is the graphical representation of this surface, 4xy minus x raised to 4 minus y raised to 4. And it is clear that at these 2 points, and what are these 2 points? One is, this is our minus 1. Okay, sorry, I think yes, this point. This is our minus 1, and similarly 1 1, that is somewhere here. Okay, at these 2 points function has a relative maxima, clear. And 0 0 is somewhere here. Yes, at this point what happened? It is clear that at this point it has a saddle point. Why? In this direction it is increasing, right? In this direction it is increasing. But what about this direction? In this direction surface is decreasing. Clear? That's why this is not a maxima nor minima. Such points are called saddle point. Clear? This is the geometry of the surface. This is your homework. Thank you.